and it's like there's no data, and I'm just sitting there, and I don't know anybody in my class. Like, I'm not that I don't know them, but I'm not friends with them.
You don't like to know them? I understand.
Yeah.
I'm the same thing. I'm the same thing with a lot of people. There's like, I know them, but I don't really kind of like to know them.
What's
I really want it.
in the front talking to
Yep. That's a long bell. Okay, so the day I warned you is here, and I'm going to tell you right off the top that I struggle with concentrations of weak oxyacids and nitrousbases. So if I get it backwards, I apologize ahead of time. So I'm probably going to get it backwards at one point.
Are you recording?
I think I am.
Are you?
I just want to make sure that you're right. I should make sure that
Yeah.
we're
Okay.
recording. Okay. So here's the deal. Everything we've learned about so far is a strong acid forms a negligible conjugate base, and a strong base forms a negligible conjugate acid. And then I think the word we're using is robust weak base makes a feeble conjugate acid, and a robust weak acid makes a feeble conjugate base. And the converse is also true. A feeble feeble weak base makes a robust conjugate acid, and a feeble weak acid makes a robust conjugate base. Okay, so those are our big rules, right? Now, you will usually be given a Ka or a Kb, and if you know the Ka of an acid, weak acid, then you know the Kb of its conjugate, and if you know the Kb of a weak base, you know the Ka of its conjugate. And what this unit asks you to do is be able to identify the relative strengths of a class of weak acids and a relative strength of the class of weak bases. Okay. And the class of acids are called oxyacids. So let me draw our classic strong acid. Our strong acid would be HCl. Okay. Strong acid, super strong. And the reason, actually, why do you think it's a crazy strong acid with a K value that's larger than 1? Ka value. Why do you think it's a strong acid?
What do you mean?
Why? Okay, so we know that there are 6 strong acids: HCl, HBr, HI, H2SO4, HNO3, and HC4ClO4. Those are our 6 strong acids. But why are they so strong?
Does it have to do anything with ionization?
It does have to do with electrons. Keep thinking. I'm just going to draw a little visual aid.
Is this what you were talking about with the sharing of the electrons between?
Yes.
Yeah. Okay.
Okay. So the chlorine, because it is so large and because it is so electronegative, hoards the electron pair that the hydrogen and the chlorine share. And the more that other thing, the A minus in this case, again, we show acids with an H and an A minus, so that's H and A. And the more the A hoards the electron pair from the bond, the stronger the acid's gonna be. So that pull of electron density away from the hydrogen determines the atoms or the acid's strength. Make sense? Now the base is also plays a role. So our classic base would of course be NH3. And the reason NH3 is our classic base is this electron pair can very easily attract the proton floating around in water. Okay. So you got water molecules chilling out. Here's the O, H, H. There's a couple of electron pairs. So water molecules, those electron pairs can grab a proton from water, making H3O. But they're no match for NH3's unshared pair here. Okay, so far so good. So bases, they want to take the proton, and the more electronegative their available end is, the stronger the base they will be.
So did you say an acid was stronger because it's the hydrogen is easily takeable?
Yes.
Okay.
There's very little electron density in the bond that's keeping the hydrogen bound to the molecule. If the electron density is pulled away, it's kind of the proton's out there exposed. And the more out there exposed it is, the stronger the acid will be. So that's what we've talked about so far. And there's our big strong acids, bases. I actually want to come back to bases because oxyacids are more important than bases. Okay. And like I said, the huge caveat, I have never seen, I cannot remember ever seeing this taught directly on the AP test, but it's in the curriculum, so it's fair game. All right, so when you look at the halogen acids, HF, HCl, HBr, HI, the HI is a stronger acid than HBr, than HCl, and they're stronger because HI has a massive massive collection of protons in the nucleus, pulling the electron density away from the bond. Now, HF is very, very electronegative, but it only has 9 protons. So it can't hoard the electron quite as strongly as HCl and HBr, which is why we say HCl, HBr, and HI are the strong acids, and HF is a weak acid. The book would say, in accordance with Coulomb's law, the greater the distance between the nucleus of the anion and its outermost electrons, the smaller the attractive force on the H+ ions. It's big, pulls it away. Weak attraction for hydrogen's protons. Because remember, a bond happens when a proton from one atom is attracted to the electron cloud of the other atom, and the proton of that atom, or protons of that atom, are attracted to the electron cloud of the first atom. So hopefully that makes sense. Okay, now with bases, when you have a I-, you have a very, very strong, very, very electronegative atoms in fluorine, chlorine, bromine, and iodine. Fluorine is the most electronegative, so it is the best, has the best pull for a wandering proton. Okay. Again, that whole fluorine being the most electronegative is coming up again. Remember electric with the intermolecular forces. So since fluorine is the most electronegative, it is got the greatest pull for an available proton, making it a pretty good base. All right. Are we good so far?
Doesn't that conflict with the idea that strong acids have negligible conjugate bases?
How so?
Or
Maybe. How so?
okay. Well, because it's saying that for these halogen acids that all their conjugate bases are negligible and are just sort of ignored, but as you know, the conjugate bases here imply some of them are stronger than others.
I see what you're saying. Yes. Okay. Yes. So when we say HCl is a strong acid with a negligible conjugate base, and here you're basically saying you have strong base strength here. Yeah, that does kind of. I can see how that directly contradicts. The principle they're talking about here is more electronegative, better base.
Okay.
Yeah. But yes,
So
Cl- by itself is not a base.
when you say acid strength increases, what does that imply?
That means the proton is more weakly held and is able to be pulled from the acid.
But wouldn't it, if an anion has a bigger radius, wouldn't that mean there's more electron density around the bond? So
Yes.
it'd be harder to grab?
Because keep in mind that it is the proton they're grabbing. So if you have more electrons, more electron density, that's more negativeness.
Oh, so the H would be farther.
Exactly.
Okay.
Yeah, they should be more exposed, if you will, to water molecules or bases. All right, so we're going to come back to conjugate bases in a second. Okay, these are oxyacids. So oxyacids are called oxyacids because they have a hydrogen bound to an oxygen and then bound to something else. Okay. The classic oxyacid that pops up all the time in the College Board is HOCl. HOCl. HOCl pops up all the time. Okay, so oxyacids are all weak acids. And they are tricky because it looks like there's a hydroxide bound to something. You're like, oh, it's just like a hydroxide. But it's not a hydroxide, it's an oxyacid, where the hydrogen is bound to the oxygen, which is then bound to the chlorine. And if we were to draw this, it would look like this. Okay, so that hydrogen is out there and exposed against a gigantic electron cloud of the oxygen and the chlorine. Now, so all oxyacids are weak, and the stronger the electronegative thing, the other thing bound to the oxygen, the stronger the oxyacid. So in other words, there's a thing bound to the oxygen. The oxygen is the bridge that allows the electron density to be pulled away. In this case, the chlorine is pulling the electron density away from oxygen, which then pulls it away from hydrogen, making the hydrogen more exposed to bases. So the more electronegative your chlorine is, or more electronegative this atom is in the oxyacid, the stronger that acid is going to be. So it's always going to be relative. If you're ever tested on it, it's always going to be relative. It's going to be like HOCl versus HOBr. Which one is going to be a stronger acid? Which of these two is going to be a stronger, more robust weak acid? Remember, the more electronegative thing connected to the oxygen, the stronger the acid is going to be.
Oh, HOCl.
Yeah, so HOCl is a more robust weak acid than HOBr. And should you find yourself seeing HOF, HOF, of course, would be the king of the oxyacids because fluorine is even more electronegative than chlorine. So again, the more, think about the electron cloud. You can realize it's like this big. But think about the electron cloud. The more electronegative this thing is, the more that electron cloud gets pulled towards the electronegative end, exposing the hydrogen to being taken by bases. Those are oxyacids.
So is this always indicated in the way that almost like written? With like HOY?
Yeah.
So what can you write it like, so would you be able to tell if it's an oxyacid based on the way it's written?
Yes. It'll always have the H in front. It'll always be HO something instead of something OH. If it puts the OH in the back, it's a base. Yeah, they are not going to try to trick you. They're not going to write HOCl, COOClOH. They won't do that. I hope. I have 95% confidence that they're not going to try to trick you. All right, and that's it. These are also oxyacids. There might be extra oxygens bound to the thing that we're focused on, but they don't change anything. They don't change they don't change the rules. All right, how are we feeling about this? All right. So there's a little diagram. HCl is more electronegative than Br is more electronegative than I. So of these three oxyacids, HOCl is going to be the more robust of the oxyacid. And then if HOCl is the more robust of the oxyacids, then OCl will be the weakest of the conjugate bases. Does that make sense? So the more robust a weak acid, the more feeble its conjugate base. I don't like how the author says conjugate base stability. No, we'll just stick with strength. Stability would be the opposite of strength. Oh, geez. Yeah, this goes too far. Again, like I said, I can't in memory remember a question about oxyacids, but this goes way too far, so we're just gonna throw that. Same thing here, throw that. By the way, the word they use is induction. In other words, induction is pulling away of charges. Like in magnetism, there's magnetic induction where you induce magnetic fields to be pulled away, or electrostatic induction where you induce electric fields. But that's the pulling away of the electron density is induction. So again, I think this is way too much. Okay, carboxylic acids are special organic acids, and the carboxyl group is C11O bound to an O here. Okay, so benzoic acid, anything that ends in oic acid is a carboxylic acid. They work pretty much the same way. The more electronegative thing pulling the electron density away from the oxygen is going to be a stronger acid. So here, there's 3 fluorines. That's going to pull the electron density further towards the fluorine. So anything that pulls the electron density away from the hydrogen is going to be stronger than something that doesn't. Capiche? Verstehen? Comprende? Eh? Gesundheit.
You're just using every language today.
I gotta. It's fun. Gotta figure out what. I mean, everyone knows like the hellos, but that's just more fun to do other things. Okay. Willkommen. Yeah. So.
Hello.
Hallo. Yes. Hallo. I had somebody with a willkommen today. Willkommen. I think I'm looking forward to somebody complaining to the administration because I greeted him in Arabic. He greeted me in Arabic. Yeah. He's a Nazi. He's a terrorist. Okay, so we don't care about the rest of that stuff. Okay, so let's backtrack a little bit. So we talked about oxyacids. How are you feeling about the concept of oxyacids?
Okay.
The idea of just pulling electrons away? Again, I think they're going to test it.
Would they?
Where's the nitrous bases?
Go
ahead.
If they might like never test this, would they ever? Because I don't really know the difference in individual structure, the difference between oxygen.
The hydrogen would go to an oxygen instead of something else.
Okay.
That's the biggest one.
Can you draw out like a strong base for OH to see the difference?
Yes.
Like any.
But strong bases are usually ionic. So, like our typical strong base is Na plus and OH
So
minus.
They would just be a bar.
Yeah. So it would be Na plus with no electrons, no outer electrons at all. Then oxygen, an H with an extra electron. That would be minus like that.
And so the HOCl would be like together. Okay.
Yeah. So oxyacids are covalently bonded.
Okay.
Yeah. This half is covalently bonded. So again, one of the weirdest concepts we like to teach, ionic and covalent, is 2 separate things. In reality, it's more of a spectrum. Okay, I thought there was a slide on nitrous bases, but I missed it. Here we go. Okay, so nitrous bases. So nitrous bases, they are all basic, and again, like I said before, again, a base is something that attracts a proton. So that double bond is what attracts a proton. So you got NH3 chilling out over there, grabs a proton, forms NH4 plus, which is its conjugate acid. So this is a weak base, NH3. This is its conjugate acid. Okay. So anything that has a lone pair can act as a base, but the AP restricts its understanding to nitrous bases. Nitrous as a adjective, not as a ion. Okay. So here, there's a proton there. If you ever hear amine, that's the big one. If you ever hear amine, it's a base. Because amine, the amine group is NH2. So you have R, N, unshared pair, H, H, and then something. So nitrogen's got its unshared pair, and then 2 bonds. So this is an amine group. Methylamine, like in Breaking Bad, it's methylamine. No, it's methylamine. Methylamine is everyone's favorite amine. It is CH3NH2. I think that's right.
How do you spell amine?
A-M-I-N-E.
Okay.
A-M-I-N-E.
Is it like a suffix?
I'm sorry, what?
Is it like a suffix?
Yes.
Okay.
Yeah. Methylamine, so on. Methylamine.
Is it French?
I love Breaking Bad. No, it's organic. So methyl basically means there's a CH3 group in front, and then amine is attached to it. So methylamine, and then they needed, like I said before, they needed a MacGuffin, so they made methylamine. You and I could make methylamine. We could do it in a syringe. You just compress ammonia and methane together, squish them together, heat them up, methylamine. He could have made it in his trailer, but yeah, they needed a MacGuffin. But anyway, so if you have 2 unshared pairs on the nitrogen, that unshared pair would really like to attract a proton, making it a pretty good base. And the trend is the strength. Yeah, that's it. Okay. So the trend is the more electronegative that unshared pair is, the stronger the base is. So if something pulls electron density away from that unshared pair, it will reduce the strength of the base. Okay. For instance, throw an example at you. So you got your methylamine. So you got your CNH. So yeah. Okay. Anyway, so this would be CH, CH, and then let's go ahead and put the amine group back in, but then let's bound it to a carbon with a bunch of fluorines attached to it. All right. So this has relatively low electronegativity in the CH3. This has a massive electronegativity in the CF3. So as far as bases go, this one is a stronger base because there's not much is pulling the electron density away from the nitrogen's unshared pairs. Does that make sense? Okay. Again, I don't think you're ever going to see it, but oxyacids, I'm going to say there's a 1 in 3 chance you're going to see oxyacids. Nitrous bases, probably a 1 in 10 chance to see nitrous bases. All right. So let's go do some exercises.
Let's do exercises.
We're doing 6 and 7. You're doing 1 through 5. Okay. Number 6. Oxyacids, HOX. Yeah, HOX. Oxyacids. May technically be still an APRM, but they haven't been seen on the test in decades. Yeah. Anyway, for HOX, the more electronegative. There you go. Draw the Lewis structure of the following acids. Identify the strongest acid in each set. Provide justification based on the electronegativity and molecular structure. drawing Lewis structures is cool. So let's go ahead and do at least one of them. Let's go ahead and do. Oh, geez. Why? Okay. Let's realize that this is a strong. That HClO4 is a strong acid, and just realize that HOCl is a weak acid, so it's definitely that one. But let's do B. So write up B and then determine of HiO3 or HiO2, which of these is going to be the stronger of the acids.
Blow it up, yo.
There we go.
Shrink it down, yo.
You ever opened an app and then just forgot why you opened it?
Yeah.
Go back to it, like, why is that open?
I'll do it multiple times. I'll close Twitter, be bored, and then open it right back up and close it again.
I've done that, except it's walking across my house. And I'm like, why did I do this?
You go to the kitchen and get some.
We don't need more potassium chlorate. It's just hidden from
The O would just be interchange.
I don't
Be a change of O.
Let's go together.
The 2023 AP exam terms and conditions are now available for you to view.
What do you mean terms and conditions?
This stuff's legal boilerplate.
Fun.
It's not available for you to view it if you are like. It's just said inform your students. So I did just now. This is
I think I know it.
still looking for my sunshine you promised during the video announcements.
We get sunshine. Is it gonna like rain? Has it rained?
They were saying it might. It does. It still says scattered. Okay, so it still says mostly cloudy on Google, but in the weather app it says chance of showers. I'm thinking it's not going to. I think it's mostly cloudy.
Yeah, it's about to be warm up 13.
All right. So, show your neighbor your Lewis structures and see if you agree with your neighbor on the Lewis structures.
This is the best thing I got. I don't know. I don't think, I'm not sure the order matters.
Oops.
Yeah, I did a similar.
Oh,
that's right. I don't think
Yeah, I don't
those
think so.
change.
So,
I'm trying to
Put
go.
those together.
No, they're all bound to the iodine.
Okay.
Iodine, right?
Yeah.
Yeah.
Yeah, so all the oxygens are bound to iodine.
And then there's one with an H.
Yeah, one with the H, other two have double bonded. So
Uh,
two of them are double bonded to the iodine, and the other one is single bonded to the iodine.
How do you know the double bond?
It's the only way the electrons work. Yeah. We got the iodine chilling out in the middle. We know there has to be an oxygen, then a hydrogen. And then we got an oxygen and an oxygen, and we're all, yeah. So the first thing we do is we put in the unshared pairs that are normally there. Oxygen being the most electronegative atom, it's going to keep its unshared pairs whenever possible. And then we have to realize that we got IO3. Or I said I'm not going to do it. I'm going to do H in front. H, IO3, like that. HI3. So we got 1 electron there, 7 electrons there, and 18 electrons there, if I remember correctly. Oxygen gets us 6 by 3. Iodine gets us 7, hydrogen gets us 1. So the good news, it's an even number, yay. So that looks like 26 electrons.
That's math.
So these are the electrons that need to be there. Again, the more electronegative atom gets to control what goes on. So it has 2 unshared pairs. So if it's not bound to something more electronegative, it doesn't have those unshared pairs broken. So let's go ahead and count. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we got 20 so far, which we need to add 6 more. We're missing 6. So we can do that a couple different ways. The putting in bonds is going to be the easiest. So this does not have an octet, and now it does. 22, 84. This does not have an octet. Now it does. 24, missing 2. And everything has an octet. We need 2 more electrons, unless I counted wrong. I might have counted wrong. Oh, no, just stack them on ID.
Yeah.
2 more electrons, stack them on ID. Okay, so boom, boom. Then it's 26, and we're done. Okay. So that's our, yeah. Okay, so yeah. So we are looking at that, and then we're going to look at the other one, which is I bound to an O, bound to an H. Again, iodine is less electronegative than oxygen. And so we got 7, so HIO. Yeah, that's 1, that's 7, and that's 6. Okay, it's a whole number again, so that's 14. So 2, 4, 6, 8. So we've got 8, need 6 more. And we can just fill up iodine.
It's HIO2.
Is it HIO2?
Yeah.
Oh, okay. Then let's put another oxygen in on the other side.
See
that.
here.
Yeah.
You save the day.
So it would add up to 18? No,
20.
20.
Yeah, so this is going to be 12
Yes.
and 20 electrons. So we've got the electrons in that we need to make it work. 2, 4, 6, 8, 10, 12, 14. And so we got 14, need 6 more. Got 14, need 6 more. And oxygen does not have its unshared pair, or it doesn't have an octet. Now it does. It's 12, we need 4 more. And oxygen here has its octet, hydrogen has its octet, iodine doesn't. We need to put 4 more in, so let's just slap a couple onto iodine. And that's that's 20. Hold on. Check my work. Always important to check your work with someone smarter than you.
14. 18.
Yep.
22. That's 22.
That's 22.
Yeah.
2, 4, 6, 8, 10, 12, 14, 16, 18.
I'm stupid.
That's all right. Your brain is just making room for the more advanced stuff and letting the little things go. Pretty soon you won't be able to talk or walk. Okay, so of HIO3 or HIO2, which is the more robust weak acid? Which of of those two is the more robust weak acid?
I assume IO3.
It is, yeah. So IO3 is this cluster of 3 oxygens around the iodine is more electronegative, pulls more of the electron density away from the hydrogen bond than this cluster of 2. So IO3 is the more robust weak acid.
If it was a base, if we're testing which one was more base, would it be it would be the one with less added on stuff, because that takes away from an unchecked pair.
Yeah, it doesn't violate the rules. A more robust weak acid will have a more feeble conjugate base. So if you're like, you chop the hydrogens off and replace them with Na, so you said, okay, let's put an Na here and an Na here, then this one, which was the stronger, more robust weak acid, would be the more feeble weak base.
Okay.
And this one, which was the more feeble weak acid, would be the more robust weak base. Okay, and just looking at this, HOPR, HBRO3, which of these is going to be the strongest of the, more robust of the weak acids? HBRO3. BRO3 is fat. We're doing number 7. Identify the strongest attributes of the following sets. Provide justification based on molecular structure. So more of the same stuff. So these are, the COO is a carboxylic acid. Again, carboxylic acids always end COO because they have something bound to a carbon. I'll show you like that. Okay. So that's why it's COOH. For a carboxylic acid, the H is at the very end instead of in the front. So carboxylic acids are all carboxylic acids of methyl carboxylic acid or trichlorocarboxylic acid. Which of these is going to be a stronger acid?
Trichloro.
Yeah, trichloro, because this whole chloro thing is very electronegative. And then CH2 single chlorine versus CH double chlorine. Which one of these two is going to be the more electronegative? Double chlorine. More electronegative then, stronger, more robust weak acid. And we continue on. Here we have iodine and 2 ethyl groups, and here we have chlorine and 2 ethyl groups. This kind of nuance is never going to be on the test. But chlorine, technically more electronegative, so it's going to be that one. And then, forget it. You got this.
So with CCl3, COOH.
CCl3.
COOH. Wouldn't that be a strong base?
It's got a hydrogen on the end, so it's a carboxylic acid. And
It's
it
not
doesn't have,
hydroxide.
it does have, okay, so good question. It does have unshared pairs, making it so it could act as a base.
Okay.
So this carboxylic acid technically could behave like a base in the presence of an acid that is stronger than it is. Okay, so that's called amphoterism, when a molecule behaves like an acid in the presence of a stronger base, or when a molecule behaves like a base in the presence of a stronger acid. Okay. Which is like water. Yeah. Well, exactly. Just like cheeks, bottle of Coke. So if you have water and you put in an acid that's stronger than H3O, that's stronger than water, it's going to behave like a base.
Okay.
If you have water, put in a base, it's going to behave like an acid.
It's just with because it has hydroxide.
Mm-hmm. No, it doesn't have a hydroxide. It has the carboxylic acid group. So it looks, I know it's super tricky.
Because it's written like that.
Yeah. Luckily, you'll always see it written this way. It's a molecularly covalently bonded compound. So if you see "coo," then it's a carboxylic acid. Again, we're kind of floating into organic chemistry at this point. But there you go. All right. So go ahead and fire off a few exercises on your own. And if you get hung up, let me know. And I will try my best not to confuse you any further. And the stream.